Hello. Today we're going to take a look at lesson number 44, half-life, which is a topic that to some extent should be kind of familiar to you if you've talked about things like exponential decay in a math class. It's the exact same thing here. So jumping right on into it then. Half-life, by definition for us in physics, is the time it takes for half of the parent atoms to transmutate into something else, because we know that as soon as we have especially some particularly highly radioactive elements, they're going to go into alpha beta decays and start transmutating into all sorts of different elements. What we're looking at specifically here is how much time it takes for exactly half of the parent atoms, the starting atoms that we have in a sample, to actually have gone through those decays. And this is a very regular process. It follows a nice statistical sort of progression that is very standardized for particular isotopes. So if we want to talk about actual values, actual numbers we can get, a value of 10 to the negative 22 seconds is highly unstable. That means that even in just 1 second, everything will basically have transmutated, have gone through lots and lots and lots of half-lives, and it's gone. There's going to be some artificially produced isotopes of unnaturally occurring elements that, yes, have this sort of a short half-life. Then you can look at something like 10 to the 28 seconds, about as stable as something can get, because that's 1,000 billion years before you get through even one half-life. We're talking things here like the very structure of things in our atoms themselves, like protons, would have a extremely long half-life, because even within the long age of our universe, no protons have gone through a decay to something simpler. Now, one thing that's always very important to remember in this, and it's easy to misinterpret and get the wrong idea, is that even though everything's going through all these transmutations, the total number of atoms that we find in the sample always stays the same. We're not destroying any matter in this process. We're just allowing it to transmutate into different atoms, different elements. So, as an example, and I'm going to keep coming back to this one again and again, we're going to talk about carbon-14, which has a half-life of 5,730 years. So, I want to look at what would happen to a sample of 1,000 carbon-14 atoms if I was able to wait around for a very long time and just kind of observe what's occurring to those atoms. So we're going to start with 1,000. Nothing's changed yet. Nothing's happened yet. There haven't been any decays yet. We're going to wait for exactly one half-life to have passed. 5,730 years. And we got to be careful here, because it's not like we sit around waiting for the clock to tick over to 5,730 years and suddenly everything all happens at once. This is a random process. It occurs over a relatively long period of time in human years, but it would steadily be happening. It's occurring all the way through. So, after 5,730 years have passed, I would expect only 500 carbon-14 atoms will remain, because it's half of what I started with, half of the 1,000. That doesn't mean the other 500 atoms have just disappeared, but they have transmutated from carbon-14 through processes like alpha or beta decays into a more stable element. Now, what happens if I wait so that 2 total half-lives have passed? It's not just one half-life, but 5,730 more years have passed. Sometimes people will incorrectly say, well, the other 500 will just transmutate into something else. But we have to think of this as almost like flipping coins up into the air. If I flipped 1,000 coins up into the air, about 500 of them would come down tails and the other 500 would be heads. But if I only pick up the 500 that landed heads and I flip them up, Not all of them are going to go tails. Again, only about half of them will go heads and the other half tails. The same thing happens in our second half-life. After a total of 11,460 years have passed, it is half of what we had at the beginning of the first half-life having passed. 500 divided by 2 is 250. It's always like we're doing a brand new throw up into the air of our atoms and seeing which land heads and which land tails. It's always half of whatever we had. And again, there's still 750 other atoms, but they're going to have been going through a bunch of alpha and beta decays now. Some of those ones that went through initial decays from the 0 to the first half-life having passed, even they will have gone through other decays now. After 3 half-lives, a total of 17,190 years, we took the 250 from 2 half-lives passing, divided by 2, we got 125, half of the previous amount. At 4 half-lives, well, this is where things kind of start to break down, because I do have to admit that a sample of 1,000 atoms really isn't that much. I think about something that's, just sitting on a table in front of me. We have to count the number of atoms using something like Avogadro's number, for those of you that play around in chemistry a bit. So these numbers are actually very, very small. But I did say 62-ish. Because I took the 125 divided by 2, got 62.5, but I can't have half an atom. So I'm saying, maybe 62, 63-ish carbon-14 atoms. And then after 5 half-lives, we're down to 31-ish carbon-14s remaining. One thing we find is that as we do this, as we go through exponential decays, after about 4 or 5 half-lives have passed, the total number of whatever remaining actually drops really low because it was exponentially dropping. So if we even look at it as sort of a graph of percentage as a function of half-lives that have passed, we get this sort of shape of graph. I didn't put the time in years on the x-axis. I'm just saying number of half-lives, because that way this graph would look the same no matter what I'm dealing with. And you can see how it really starts to flatten out after about 5 half-lives. That means that whenever we do something with half-lives, it kind of becomes unreliable after about 5 half-lives, because the little changes that we're seeing could start to really be due to random chance. Kind of like if you've got only 2 or 3 coins left, you could flip them and get all heads several times before a tail would pop up. And that's just because the sample size is really small. So how does this figure in with something like carbon dating, which is linked in so much to that carbon-14 I was talking about? Carbon dating is exclusively something that's used with any sort of a plant material that at one point was alive. Because if we think of classic photosynthesis, carbon dioxide is going in, the whole process of photosynthesis, it uses energy from the sun, and it releases oxygen. In the most basic sense here, that tree is made out of carbon because it holds on to the carbon. And I know there's other stuff going on with glucose and hydrogens and all that sort of stuff, but I'm looking at just how it has captured carbon out of the air. So if I'm looking at maybe a piece of wood that was made into a spear or an amulet or something like that that's buried with somebody, when that was initially cut off a tree and made into something, it had, let's just say, for example, 1 million carbon atoms in it. Because of the natural abundances of the different isotopes of carbon, I know about 989,300 of those atoms will be carbon-12, and only about 100 of them will be carbon-14. And yes, I know if you add those numbers up together, you don't get 1 million. That's because there's other isotopes also. But the only two that I'm noticing, the only two that I care about right now, are the carbon-12 and the carbon-14s. Because that person dies, they get put into a tomb with their spear or whatever it was that was made out of wood, and they stay there for the next few centuries until somebody comes along and digs up that tomb and finds the remains and finds something that was originally based on plant material, whether that is like the spear made from wood or linen that was wrapped around the body, because linen is made from flax, which is a plant that grows very much like wheat grows. Anyways, it's many, many years later, and we find that artifact and we put it through a mass spectrometer, a device for separating out isotopes of different masses, and we find that there are 989,300 atoms of carbon-12. Yep, that number stayed the same because carbon-12 is so darn stable, its half-life is really long, that it hasn't had a chance to really have anything decay yet. But I look at my carbon-14s and I find there's only 50. Now, I know based on the 989,300 atoms of carbon-12, that's like my baseline, that there should be 100 atoms of carbon-14. So if there's only 50 found, that means that the carbon-14 must have gone through exactly-ish one half-life. That means that that piece of wood is about 5,730 years old, which means probably it was buried with somebody right from around the same time period. This tomb and the artifacts I now know are approximately 5,730 years old. And we don't even have to wait for one exact half-life. If I'd found that it had 75 atoms or 80 atoms of carbon-14, I could still date it, but we do want quite a bit of time to pass for something like carbon dating in this sense to be more accurate. Now, this does lead us to the half-life formula, which, if you think about formulas you've seen for exponential decay in math, look very similar. But this is the way that we're looking at it and the way that it's presented on our Physics 30 datasheet. So, in this formula, capital N on the left is the amount remaining of something. The NO is the original amount, and little n, the exponent in the top right, is the number of half-lives that have passed. Now we got to be careful here. N and NO can actually be measured in any units you want, as long as you make them both the same. So it could be number of atoms, or it could be the mass, like in grams or kilograms. It can even be activity, something we're going to talk about soon. But you just have to make sure that capital N and capital N naught are both measured in the same units. Now, little n at the top there, you have to be careful. That's not the amount of time that has passed. It's the number of half-lives. So quite often, we end up doing a little calculation there because we have to take the amount of time that has passed, actually passed, divided by the time in one half-life to get the number of half-lives. This will probably look a little bit easier if we can see an example. So I tell you that Marie Curie is in her laboratory and she isolates a sample of polonium-210, which has a half-life of 138 days. It's relatively quick in sort of human terms, not like, microseconds or something, but still, 138 days isn't that long. The sample she's got is 765 grams of polonium-210. She puts it in a box, she puts it off to the side, and forgets about it while she goes and does some refining of radium. 3.8 years later, she takes down that box, and we want to know how much of the original polonium-210 is still in the box. So, first thing we're going to do is we're going to convert the number of years that have passed into days. That way we can use it with the half-life being 138 days. We're going to have to use our calculations where we have to use units that are the same. So I wrote it as 3.8 annum. Annum is just a fancy way of saying years, times 365 days per 1 year. Don't worry about half-lives and stuff. This is good enough an estimate for us. So we find out that 1,387 days have passed. And yeah, that's not just by fluke. I've set it up that way for us so that we can take 1,387 days, but compare it to polonium-10's half-life of one half-life each 138 days, and I find that the number of half-lives, little n, is about 10.050 blah 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 blah. It's about 10 half-lives have passed. I grab my formula for half-life, and I usually in the brackets replace 1 over 2 with 0.5. Just remember, the reason on your data sheet that it's shown as 1 over 2 is because a fraction is perfect. It has infinite number of sigdigs. That 0.5 is still something I'm treating as infinite sigdigs. I'm going to look at the numbers I'm substituting in from the question to figure out how many sigdigs I should be allowed to have at the end. So NO is 965 grams, the original amount I started with, times 0.5 to the power of, now I would actually enter this in as the 10.05072, blah, 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 blah. And it's easy to do that on a modern calculator because most of them have a button that lets you do exponents really fast and easy. It might even have, like on a TI-83 or 84 or Inspire, the symbol that some people call the hat symbol or the roof symbol. But I type it in with all of those unrounded 10.050 blah, 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 and I get an answer. And here's where I'm going to round off for sigdigs. And I'm really just kind of looking back that one of my numbers was 3.8 years, only had 2 sigdigs, so I'm kind of safest with rounding off to 2 sigdigs in my final answer, 0.72 grams. Same units as my original amount was. I'm measuring in grams for the original amount of my sample, so grams for my what's left also. Now, something I quite often get asked is, but what if we have to solve for a different variable in this formula? For example, what if I needed to know the number of half-lives? So it'd be a question like this, where I tell you that we're starting with 75 grams of lead-212. I know that it has a half-life of only 10.6 hours, and I want to know how long it's going to take until only 9.3 grams remains. Well, if I wrote this out using the half-life formula, it would look something like this. 9.3 is what I'm left with, 75 is what I started with, and I need to find little n, the exponent. Now, the reason why this can be kind of sticky for us is, if you know stuff about math, you know that the only way to solve for little n there is to use logarithms, which, if you set it up with logarithms, you'd start solving it like I'm showing there. And if you're comfortable with that, if you get that, please go right ahead. You can do a logarithm style method, but I'm not trying to teach it to you here, and I'm also telling you we can't require you to do it this way. We have to give you a different way. Now, I do want you to notice that if I did do the logarithm method, I do get a little n value, number of half-lives, of just over 3 half-lives. Just kind of keep that number in mind for a moment, okay? So this is the way you'd be expected to do it without getting the logarithm stuff. On your calculator, start with 75. That's the amount we started with, and divide it by 2. That would be 37.5 grams remaining after 1 half-life has passed. That's not the number I want. Divide by 2 again, and I get 18.75 grams. That's how much is left after 2 half-lives have passed. Still not what I want. Divide by 2 again, and I get 9.375 grams. That's how much is left after 3 half-lives. Hey, that's actually pretty close to the 9.3 grams that I was told I'm looking for, how much time it takes to get to that amount. Now, I know this doesn't seem perfect, and it's like I'm cheating almost. I'm only getting a close to amount. That's all we're expected. I know that about 3 half-lives have happened, and each half-life is 10.6 hours, so I take 3 times the 10.6 hours, and I find out that it's 31.8 hours. I bet you this is a multiple choice question, and one of the answers is 32 hours. You pick the answer that's the best or the closest. Now, if you went back to that number that you got from doing the calculation using logarithms, you'd still get about 32 hours because you'd still have to take that times the 10.6 hours in each half-life to find out how much time has actually passed. Now, activity. I said this was, soon to come sort of thing. Activity is just a measurement of how many nuclei are decaying per second. If you really think about it, that means that what we're really just measuring here is frequency, because frequency is somethings per second. But specifically when we're looking at radioactive decays and we're measuring how many decays happened in each second, which can also just be called the decay rate, we will refer to it using this special term instead of just saying frequency. But you can always keep in the back of your head that you can treat it like a frequency. I don't want to get away from it, but you could actually measure this in hertz, although we don't. We measure it in becquerels. And we're just trying to do this to honor the work of Henry Becquerel and his initial discoveries of radioactivity. So, good on him. But when you're talking about sort of like classic movie, hearing this thing that they'll call a Geiger counter, which is actually a Geiger-Müller tube, and it only picks up ionizing forms of radiation. That device is technically measuring activity. That click and it going more rapidly seems scary, right? That's because you're measuring the activity, how many decays per second are happening. And if something is more radioactive, giving off more radiation because it's going through more decays per second, its activity is higher, that's something we want to be worried about. The great thing for us is that activity also follows the rule of half-lives. And it makes sense because if you've got a sample and it's gone through a full half-life, half of its whatevers have gone through their decays, there's less to continue doing the decays, so the activity drops off as well. So that's why we can use the half-life formula for numbers of atoms, grams of material, becquerels of activity, and it all follows the same rules. Now, there is a video that is in the slideshow that if you do want to watch it and see another perspective of half-life, that's great. But otherwise, that's the end of this section, and I wish you the best of luck. Have a good day.